us not start. Okay, so let us start. It's my great pleasure to introduce Grebík, who I know for a couple of years, but I accidentally ran to him last Friday in the library here. I was Grebík, currently from Universität Leipzig. And when I met him on Friday, I was like, oh, how often are you in Prague? And maybe give a seminar. And then I took the elevator up here right after I met with Honza. And, oh, we lost a speaker. Do you have any replacement for next Monday? The organizers are asking. So it's so great. I mean, it's so great to have you here. Yeah, really looking forward to translational monotilings. And even more big kudos for agreeing with such a short notice.
Yeah, thank you. So thank you for the invitation. I will talk about translational monotilings. So let me start with the main definition, which I think that you all maybe seen. So in the discrete case, so basically we want to tile the lattice ZD by a finite set, and we only allow translations. So we say that F, which is finite, a subset of ZD, is a tile if there exists something called either a tiling complement or simply a tiling. So if there exists T, which is also a subset of ZD, okay, so this is finite, such that the following equation is satisfied. So what does this mean? So this should be interpreted as the disjoint union of shifts of translates of F by T, and T are the elements in this T, right? So this means a disjoint union. So we have some shape F. So we can, for example, consider the shape to be just these four elements, which are subset of Z2, Z square. So let's say 0, 0, 1, 0, 0, 1, and 1, 1. And now we have like this set is a tile because there exists a set of translates T, so that you can cover Z square by disjoint copies of this shape. Right? Okay, so this is the main definition. Yeah.
Maybe do they overlap or they can't overlap?
So they cannot overlap, and this is like this symbol means a disjoint union.
Oh, okay.
So this means that F plus T intersection F plus T prime has to be empty for every T that is not equal to T prime. Okay, so this set is called a tile. This will be referred to as a tiling. Okay, so we will actually need also the continuous version of this definition that will be maybe used at the end. So the continuous version of this definition is the following. So we say that measurable set, so omega, which is a subset of RD, so bounded and of finite non-zero measure, of finite positive measure, is a tile if there exists a tiling, so again P, this time it's subset of R to the D, such that, and now I will write the same equation, but because we are in the continuous setup, this is now interpreted as disjoint union up to null sets, so almost surely of these shifts, right? So this means that if you take two different elements and you shift omega, they will intersect in a null set. So this is the main definition. So we will be now interested in some basic questions, or I will tell you some known results that resolve some basic questions. For example, can we decide, I mean, this question is actually not really answered yet, but can we decide whether a given set F is a tile? Or can we understand what measurable set could be tiles?
Do we need to cover still the wall RD, or is again up to
Yeah, so both like these conditions are basically equivalent. So let's say that we want to cover it.
So they almost surely don't overlap. That's the requirement.
Yes. So I mean, two different shifts overlap in an null set.
Yeah.
Okay, or another question that is studied in this area is, what can we say about T? So assume that we have F that is a tile, and then we have this tiling complement. So can we somehow say anything about the structure of T? Can T be periodic, or this type of questions? Okay, so let me maybe emphasize that this is different. And I don't know much about other cases, so this is different than this like this domino problem or the Wang tiling problem, where we have more shapes. So basically, questions about this, like around this Wang tiling problem, asks whether if you are given finite number of these Fs, whether you can tile with them. And these questions are much more understood, and basically it's very complicated. So like in these questions, it's basically undecidable when you have such a generality that you allow more than one tile. And so that's why I stress that I talk about monotilings, that I have only one shape. It's like a big difference. And this is also different from, maybe you've seen in some of these popular magazines, that they recently discovered this aperiodic monotile. So this in R2. And here the difference is that they don't allow only translations, so here they allow also rotations. Yeah, so basically these are different words than from what I want to talk about, and very often people are confused. I the whole time talk about this question, and then they tell me at the end, but they discovered this aperiodic monotile. So how is it connected with what you talk about? So I just want to stress that when you allow rotations, it's basically the same as having this shape, and all the possible rotations, you can consider it as a multi-tile set. So you can consider it as a couple of different shapes, which is more related to this problem when you actually are allowed to have more shapes. Okay, so I hope that the setup is clear. And now let me state the main question. Okay, so let me maybe erase this so make sure that we are on the same page. So there is a result of Newman. So Newman. I forgot if there are two ends or just one end. Just one end. From 77. And so Newman proved that if you are in the dimension 1 and you tile, then the tiling set is periodic. Right? So he proved that whenever you tile the line Z, then T is periodic. Right, so what does it mean to be periodic? Well, periodic just means that that the set of those elements in Z, such that if you shift T by such element, you get T again. That this set is a non-trivial subgroup. It's like not equal to the empty or to the zero subgroup. So this is a subgroup, and if it's non-trivial, then this set is called period. Okay, so Newman proved this thing, and actually this is like a simple observation. So maybe let me sketch just like very briefly the idea how to prove this. So basically, consider the following. So if you already know, so the observation is that if some S has the property that if you consider these shifts and they are disjoint, F plus S. So this S, it doesn't mean that I am covering the whole thing. I just maybe have some finite set S, and I just shift around F. And if S has the property that these things are disjoint and cover interval I, which is a subset of Z of length at least the diameter of F, or maybe 2 times the diameter of F, then if there exists some T that extends S and it's a tiling, then it's uniquely determined. Then T is uniquely determined. Right, so imagine that there is this interval I, and there are these translates of F that somehow tile it. And maybe this S also, maybe it's also something.
It's not.
Right, so if these are the translates, let's say that these are the elements of S. This is F. These are S. So if we tile, or if we cover this interval I, which is bigger than the diameter, or maybe 2 times the diameter, then the way how you can extend, the way how you can like put another copies of F here is uniquely determined. So this is some observation in the dimension 1. And you can use this observation to prove using pigeonhole principle Newman's theorem. And somehow this theorem suggests that there is some like that these tilings complements, at least in dimension 1, have some strong structure, namely that they are periodic. Okay, so motivated from some actually functional analysis, people wanted to understand to what extent this theorem extends to higher dimensions, and it was in 1996. Lagarius and Wang. I think it was these two guys. they stated the periodic tiling conjecture. So this is a periodic So basically, in the dimension 1, you know that every tiling is periodic, but it's clearly not true for higher dimensions. For example, if you consider this example that was here, if you have this square, then you can tile in a way that are not periodic. So basically, you can tile like columns, and then you can randomly distort the columns. This will be still a tiling, but it will not be periodic. But they conjecture that if F is a tile, then there exists a tiling complement that will be periodic. Right? So the conjecture states that if F is a tile, so this implicitly means that there exists some tiling complement, then there exists a tiling so we tile and T is periodic. So here periodic in this generality means, so this means that again, if you consider the subgroup of all translates in ZD that fix T, so T plus V is equal to T, then this is a subgroup that has like full rank, or a subgroup with the property that the quotient is finite. So subgroup that has full rank. Or people can also say that it's a lattice, like a sublattice. So for example, if you are in Z2, it cannot be that there is just one dimensional period. There has to be like 2 dimensions in order to say that it's periodic. Okay, so this is a conjecture that was very influential because it has connections to 2 areas. So the one area is that, so it's also abbreviated as PTC. So PTC, if it is true, implies decidability. So basically, if you now would consider, if you would know that in some dimension D, PTC hold, then there is an algorithm that given F would tell you whether you tile or not, whether F is a tile or not.
But wouldn't you need like a bound on like how the period large can be for decidability?
No, for decidability not, because I'm just, I don't care where the algorithm stops. I will basically try and I will try bigger and bigger rectangles, and either I will have a certificate that I tile, or I have a certificate that I don't.
What's more called decidability?
So
for me, decidable means that an algorithm stops and says yes or no.
Yeah. So as I said, but I don't know when. I can guarantee that it will stop and say yes or no, but I cannot guarantee when.
Stop?
Sorry?
Because how can you guarantee it will stop based on the conjecture?
Okay, so basically by some compactness. So if it is not a tile, that there exists a large cube that cannot be disjointly covered. This is by compactness. Right? That you cannot cover. Like if you can cover every cube disjointly, then there exists a tiling. So if it is not a tile, then there is a cube that you cannot tile, and then you can produce a certificate, but I don't know how long I have to wait. And if this holds, then I can find like large cube where the boundary will be periodic, and then I have a certificate that I can copy paste.
But so does it give you positive answer in finite time?
Yeah, I mean this conjecture does. If you don't have the conjecture, then it's unclear.
No, but if I test larger and larger cubes, and I have to test all of them,
No, so like if it's not a tile, I will test larger and larger cubes, and I will see a certificate that after finite time I cannot cover this cube disjointly. And if it is a tile and this holds, then I know that there is some cube that I can tile with. So there is a cube that will be basically like the endpoints or the vertices of this cube will be element of this subgroup. And then I can just find a tiling of this large cube with periodic boundary. And this will be a certificate that if I now copy paste this cube next to each other, it will be. Okay, so this is one motivation, but then there was another motivation to something called Zᵈ conjecture. Which is something in functional analysis, and I will not say anything about it. Okay. So
this is similar conjecture for complete again.
No. So Zᵈ conjecture is wrong. It's known to be wrong in dimension greater than 3. And in dimension 2 and 1, it's completely open. Like they don't know anything. So, yeah. They don't know. Okay, so now I wanted to briefly tell you what is known and what is not known, or what is the status of this case. And then my main goal actually was, or still is, to present you. So having this PTC can be viewed as some kind of like a structure theorem. That if you are a tile, you can find a very much structured tile. And there is a very nice combinatorial result that holds in all dimensions. That's called the dilation lemma. And basically the main goal of what I'm telling you today is to present this dilation lemma that is due to Greenfeld and Tao. And then, I mean, built on results of many other people, but the version is due to Greenfeld and Tao. And then at the end, I will briefly mention some applications of this dilation. Okay, so let me start with some history of this PTC. So as I said, Newman proved it in dimension 1 in 77, and then in 2020, Bhattacharya proved that PTC holds in Z square. It was actually relatively recently, and it's basically the only positive result. And then there were 2 very big negative results. So Greenfeld and Tao in 24 showed that PTC does not hold for large B.
What is that?
Like it's not known for 3. I think it's something around 100, but they didn't optimize it. But then they also proved, and this is also very interesting, in another paper, also in 24, that monotilings are undecidable. In the following sense. So there is no algorithm that gets on input B and a finite subset of ZD and outputs whether it's a tile. Whether it is a tile or not. So somehow it's actually not known if there is a single dimension. So they know that PTC doesn't hold for large dimension, but they don't know if this implies undecidability for a single dimension. They can just prove that if the input is both the number and the shape, then it's undecidable. Okay. So these are some big recent results. And let me maybe write here that this. Okay. Okay, so let's maybe write quickly here this Newman 77. I mean something stronger, but let's say PTC holds for Z. And in R, this is also Lagarius and Wang. And this is like much more complicated, but PTC holds in R as well. And here I mean for measurable tiles, so like for measurable shapes, as I defined it in the beginning. And here the best result is Kenyon, which is in 92. The PTC holds for topological disks. In R2. And of course, this result also gives a counterexample. I mean, one can define, I didn't define it, but one can define the periodic tiling conjecture also in RD by basically replacing everywhere ZD by RD. Okay, so this is the state of the art. And so what I was interested in recently was whether we can actually extend this result in Z2 to the whole of R2. Right, so Kenyon says that it holds for topological disks, but we would like to. So in particular, it holds for some connected subsets of R2, but we are interested like to what generality we can actually get PTC in R2. And so yeah, and so the main tool in proving positive results will be what I will tell you next, which is the dilation. So, are there any questions about this historical?
So for the discrete case, it implies the algorithm. For the continuous case, is that any like? I mean, how would you even get an input of a set of RD, right?
Yeah, so I wanted to.
Any connections to an algorithm?
Yeah, I wanted to talk about this at the end, but I don't think that I will have time. So basically, what we are only able to do in the end is some polygonal sets which has axis parallel edges, but they can be disconnected and they can have holes and stuff like that. And then this PTC give you that there is some certificate in finite time, basically very similar to what I said. But the algorithm needs to use as a black box. If you basically sum up a couple of these vertices, whether this sum is equal to some other sum when you sum up the vertices. And it's like not entirely, I mean, first of all, it's not entirely clear how to encode these irrational numbers. And also, when you have these irrational numbers, it doesn't imply that you can decide these sums. So we need something stronger. We need numbers, and also they're deciding if their finite sum are the same or not. And then you can have some similar finite certificate, whether it's a tile. But for general measurable sets, I don't know. Like, that's, I don't know, like how would you get it as on the input? That's not clear. Okay, so now I will tell you about this dilation lemma, which is amazing result, which is completely elementary, but it's behind every positive result in this area. So if you remember anything from this talk, you should remember to find this dilation lemma and try to prove it or read the proof. Dilation lemma. So, okay, so I will now spend 1 minute writing who contributed to this lemma. So there is a result of Tiedemann in 95, then Szegedi 98. And as far as I understood, they were all improving some dilation phenomenon, and then at the end we will have a very short and very powerful statement. Okay, so research in 17, then there is Kari and Sabadosh. 20, then Bhattacharya, which is Bhattacharya. 20, and then Greenfeld and Tao. 21. So let F be a finite subset in ZD such that it contains the origin and it's a tile. So it's a tile with this concrete tiling complement P. Right, so this is the assumption. So we have a tile, it contains the origin, and then we have this tiling complement. Sorry? Yes, D. Okay, and now we take a number. So take any number Q, and it can be even negative, that is coprime to the size of the tile. And then you can dilate F. So then if you dilate F by Q, then the same tiling complement actually tiles. So what is this? So F to the Q is just, for every F in F, you just sum it Q times.
It's more like multiplication by Q.
Sorry? Yeah, it's okay, so an example. So if this was this cube from the beginning, so this is 0, 0. Then if you take some number that is coprime to 4, like 3.
Oh, you said that Q can be negative? This is really strange.
Then it will be like minus Q times F.
Okay. Can you swap again by once?
Ah, yes.
Yes.
So if Q is 3, then this will be again 0, 0. But now this time we will not have this point. Okay, so we will not have this point, but we will have this point. And we will again not have this point. So let me make a little bit here. So this is now your tile. And I'm just saying that the same tiling complement would work. I'm not saying that this tiling complement is periodic or anything. I'm just saying that the same tiling complement would work. And I'm also not saying anything about F. So F can be completely crazy. it can be like very much disconnected set, and this is still possible.
And it's the same type of that.
It's the same
That's the magic.
That's the magic, yes. So in particular, as 0 is in F, you can somehow view always this point as the element, as the shift, right? Like when you have the tiling, you can view this as the shift. And this dilation tells you that the dilates, they will never intersect this fixed set T. So in some sense, if the dilation is extremely big, it's still like the shape of this set T somehow still communicates with the origin in some sense. So like, okay, so this is the result, and maybe the first application, the first observation would be that if F is a tile, then there does not exist any local algorithm producing T. Right, because local algorithm somehow has this property that it's local. So by local algorithm producing T, I mean that you will run some procedure in the lattice, and at each point you will this algorithm will just look into some finite neighborhood, and it will decide whether this point will be in T or not. And now I'm saying that these dilates somehow imply that the elements in T, they need to communicate with each other even on like very large distances. So there is some like no correlation decay or something, like some fancy word like that. So this lemma already very strongly.
So can you explain what's the input of the algorithm again?
So somehow I got promised that this F tiles.
Okay.
And now I mean now I have the lattice, and for example every point has access to independent randomness, and it will in the lattice start to explore a neighborhood, and it will need to decide whether this point will be in
What
T.
does it say in the neighborhood?
Like the lattice and the other independent randomness. Somehow, it's like a, this is like a very strong thing if you can solve problems with this type of local.
So you're trying to avoid that the point would know its coordinates in this way, or?
Yeah, yes. So it doesn't know the coordinate. It only has access to this randomness and the randomness of the neighbors as it starts to explore. And then the claim is that there is no algorithm that would always stop at finite time and decide whether this point belongs to T or not.
And
So this should follow from the lemma, right?
Yes, this is
Because
right.
you can always like make it outside.
Yes. I mean, you make it as large as you want, and then you know that these points, they cannot intersect T, because T is somehow always, like if there was another, if this was shifted by this, let's say. So if this was some element of T, let's say T1, and this was the other element of T, let's say T2, then this has to stay to be element T2, right? This will be still T1 because T doesn't change. So no dilate can hit this. So that's okay. Maybe it was too quick, but just saying that this puts some strong restrictions on the structure of T. It's not local.
But okay, let me ask the question I wanted to ask. So if you get the tile, and now everybody knows where coordinate is, can you produce T?
I mean, if everybody knows the coordinates, then I mean, yes, right? Because I know that it exists, so I can just.
Yeah, how? I mean, okay, I guarantee you it exists, but I still don't see how we would produce T. Like basically what I want you, like you have the tile F, and the point knows its coordinates, and it should say like, what is its position in F.
So somehow, like in these algorithms that I wanted to mention, locally you can use like as much power as you want. So for example, they can all, if you have this square, they can all before agree that they want to use this. If they want to use this normal lattice tiling, And if they then, after that, have access to actually know what is their position in the lattice, they can call this lattice tiling and decide whether they belong to it.
Yeah, but you don't know like how the tiling will look. It can be quite. I mean, you only guaranteed Weser tiling, right? And it can be quite crazy.
Yeah, but maybe they can agree on this whole information in the beginning, and then the coordinates will help them. But I mean, this was not my point. My point was that if there is some algorithm that I don't know the coordinates, I just want to use some local randomness. This is not possible.
Yeah, but the periodic tiling conjecture is not known for these two, if I remember correctly what you said.
For
it's not known for these two, like the periodic.
No, for these two it is.
But okay, it fails for the sufficient dilation.
Yes.
Yeah, but when I mean basically what I maybe I'm like stealing your time. But what I don't see is like if I have a sufficient dilation, I guess from Greenfeld and Tao's result, like how an algorithm would even have access to coordinates would be able to tell me like what's the position, like okay, I get the point, I get the tile, and tell me where within the tile.
Okay, yeah, that's I mean if
exactly, it is not unique, and even if it was unique, like even if you keep computing, like you may have like different tilings of the origin, and you don't know which one will eventually extend to infinity. Yeah, that's my problem. Yeah,
I agree what you're saying. That I see what you're saying, but I didn't mean that, and I think that to agree on something, we would need to make precise what is the power that the locality can use. So if the locality can be that they all before find the tiling and agree on it.
Yeah, but how do you find the tiling before? That's my issue. Because if it's periodic, then I understand you keep computing. At some point, you get something which is periodic and you can extend. But if you don't know when there would be eventually a period when I don't know, I have no idea. Like even if you have like how to agree on the tiling in advance.
Yeah, I don't know. Yeah.
Is that even like requisite or something like that? Can you even like enumerate possibility?
I mean, it's not known if it is decidable or not, right? So maybe if it is decidable, even if the PTC doesn't hold, there is some structure that is hidden that you can use.
Do you have a promise it's a tile?
I mean,
okay, but you want to continue?
Yes. Okay, okay, so let me maybe. Yeah, so not much time.
5 minutes.
So I will probably just state some results that we could prove. Yeah, so this is our main tool that we are using, and what we want to understand is does PTC holds in R square. And so the main trouble, as it turns out, is that in ZD, like locally, you always see finitely many possible configurations. And this is like not really true in R2. Maybe you can come up with some example where the reason is trivial. But somehow it turns out that this is like a very annoying and in some sense a fundamental obstacle. And yeah.
How do you take a co-prime number of a tile that what is the metric for your tiles in R?
Yeah, so I'm saying that we are using this as a tool. I am not saying that there is any continuous version of it.
Okay.
Yes. So that's part of the problem.
Okay.
So what we only can do is that we somehow are in the continuous setup and we approximate it to be in this setup. Okay, so Okay, so I will just state the theorem and then I will try to explain the words in the theorem. So what we can prove with, so this is with Diaz, with Greenfeld and with Madrid. Okay, so we can prove the following. So omega, which is subset of R2, and now axis parallel, polygonal set. So, like, it's a polygonal set, so it looks something like this. There is no restriction on these vertices. They can be irrational, and also it can have holes, right? So this is the, for example, set, and it can also be disconnected. So maybe the set looks like this. So union of these things is the set. Right.
So it means it's finite union of rectangles.
Yes. Of this generalized polygon.
General.
There can also be something inside it. Yes. Finite.
But I guess that's an equivalent characterization. No?
Sorry, say again?
I mean, I agree that it's a finite union of rectangles.
Yes.
But maybe I'm overlooking something.
No. Yes.
Axis parallel thing.
Yeah. So I will now say something about tilings. If this is a tile, what happens? Okay. So I have such a set, and now I assume that it's a tile. It's a tile. And I also assume that this T is topologically minimal. Which is some property that I might explain later. So then the following holds. So first of all, T is weakly periodic. Okay, so maybe let's not say this because I didn't define it. So maybe let's just say the other property. So then we can write T to be like disjoint union of, let's say, m many sets, such that each of these pieces is periodic and invariant, let's say, without loss of generality in the vertical direction. So basically, we have this topological minimal tiling, and we can split it into finitely many pieces that will behave basically like a discrete. That's what I want to say. So these pieces that we split it into will be periodic and invariant in one of the directions. This Ti has finite local complexity. So this is for every I of m. Yes, okay, and I mean, so this is some structure theorem saying that if you pass through a topologically minimal tiling of these sets, then you basically split into some structure pieces. That so this altogether somehow is very close to be a discrete. It's close. Like each piece, each Ti is close to be discrete, to be like discrete. And somehow as a corollary.
So before you state the corollary, can you explain the adjectives? So periodic, I think it's important you put the omega there. Like you're not claiming Ti to be periodic
Yes.
itself. It's only omega after the shift of Ti. I'm just checking what I do appreciate.
Yes.
Okay. What is this invariance again?
So this invariance means that as a set, it's closed under vertical cosets. So basically,
For
this
us,
thing
we
looks
don't
like
understand what
a couple of these columns, like a union of some columns. This is how this thing will look.
So the second is stronger than the first?
The second says that one of the periods is actually can be made the whole R.
I see. Okay, very good. And periodic means it's two-dimensional.
Yes. So okay. So it's a union of columns, and these columns are periodic.
But when I don't appreciate why you have omega plus T, okay, I'm still confused. So,
But what you said is that you cannot assume that Ti be periodic, right? That this would be too strong.
Oh, I think you're telling me whether the gaps between these columns are the same.
I mean, they are periodic, so they can maybe not be the same, but they will.
Yeah, exactly.
Yes,
That's the
Yes,
first part.
yes.
Okay, and the finite local complexity means it's computable by local algorithm.
No, the final. So this is like what I tried to briefly describe. That in ZD, when you have a tiling and you look around, you always see only finitely many pictures. And here, because it's continuous, you theoretically could see infinitely many pictures. But this is not true. Like this says that for every R, I mean, I can write the definition. So for every R, if you look at, okay, so you take neighborhood of any
I can
point.
imagine what it means.
Okay.
You don't have to say it because of me unless somebody else wishes it. But I will have, sorry, I will still torture you with one more question and will let you state the corollary. Is this non-trivial? Because if the piece is kind of like a finite union of rectangles, like basically like, it's kind of, you cannot like squeeze too many things. Like, I mean, it seems like almost trivial, the second part.
Yes, so it's not, yes. Like for that, you need to do this topologically minimal thing. And you actually need to somehow, so basically what you do is that you define these decompositions, then it's very hard to prove that they are periodic. And then if it does not have finite local complexity, then you pass to some topologically minimal subtiling, let's say. And then it will split into further pieces. And you just keep repeating this infinitely, and this at some point will stabilize this. So this is like this part is the difficult. I mean, both are difficult. Okay, but let me just state very quickly the corollary. So the corollary is that we unfortunately cannot get this PTC, but what we can prove is that if omega S above is a tile, then there exists a tiling. Then there exists a tiling such that S can be decomposed into finitely many pieces, and each are periodic. Where Si is like fully periodic for every n. So they are periodic, but the lattices, they can be different theoretically. The lattices can be different. So we don't really have an example where they have to be different, but this is like a weaker form of this periodic tiling conjecture, that you can find something that splits into periodic pieces. So maybe I stated it in a way that it seems that from this, because you are basically like discrete, this is a corollary, but this needs also a lot of work. But I mean, this is the difficult part. This then it's not that difficult. But we don't know how to extend this to anything beyond this case. So that's it. So, thank you.
There are a lot of questions. One or two more quick questions, and then very interesting to discussion after.
There was silly one, but I mean, the analytic lemma, that was the condition for Q being co-prime. Okay, so it feels like if Q is actually not co-prime, you should be able to divide instead of multiply. You know, like actually shrink. Feels like you, by being co-prime, you're getting big, spreading out. So if you are co-prime, you're not co-prime. So is there like a co-dilation or?
No, but I mean, like in this discrete case, you know, like what would that be?
Right. You're right. Okay.
I mean, you would probably just intersect some of these t's.
Size, distance.
But the surprising thing is that this has like 3-line proof or 5-line proof. If you somehow phrase this in the right language, using something called convolution. But it's like so powerful that all the results basically use this.
I wanted to ask, like, we don't know whether there is always a periodic tiling. Do we have some example of some tiling that is not periodic, but still can be described as kind of recursive? So there is a description using, say, some Turing machine that if you give it coordinates, it will tell you where is it in the tiling or.
Computable subset.
Yeah, I don't know. I don't know what, like, I think what they construct is, they produce something that does not satisfy this PTC, but I think that it satisfies a lot of periodicity, that you can split it into finitely many pieces, and each piece is periodic in some direction. Or maybe in D.
So this is kind of similar to your or
I mean, there is actually one extra property that I didn't say, and yes, it is something like that. So this property would be that this T itself can be split into finitely many pieces, which would be finer than these pieces, and each piece will be periodic in some direction. But what they prove, I think, is that if you have D, then you will be periodic in D minus 1 direction. So it's like almost being periodic, but not. You split into finitely many pieces, and each is D minus 1 periodic. And I don't know if this implies anything about example that has computed. Yeah.
Okay. Thank you.
Okay, I guess let's thank Honza again.